Now we will discuss about the infrared spectra technique and instrumentation. For infrared spectrometry. So this, this So I will be going into from here, not write all those things in here. So instrumentation techniques and instrumentation. Of IR spectrometry techniques and instrumentation of IR spectrometer. So this is a simple topic. So I will be discussing the important parts of this spectrometer, IR spectrometer. So first one is source. Okay, source is some form of filament which is maintained at very hot temperature, which can be red or white heat by an electric current. Okay, I'm going to write all those things. So this will be I'm just writing its very short form. So a form of filament maintained at high temperature, which means that it will be in red or white color. Okay, it's very high temperature. Hotness will be very high, and through high temperature through electric current. Electric current. So by applying some current, we will make this filament at a high temperature, or it's very hot, and it will be in red or reddish color or in white color. Okay? So that will produce IR radiation. That is the source of IR spectrometer. So that's a filament. Uh, so that will be maintained at high. High temperature means that the it will be at red or white heat, red or white heat. Now there are two different filaments that we can use in this particular uh, IR source. One is Nernst filament. Have heard about these things because we normally use these things. So first one is Nernst filament. So this is consists of a spindle or rare earth oxide. So rare earth oxide. And one more thing about this is that this filament has to be preheated. So this spindle that will be having about 1 inch long. So I should say oxide of about 1 inch long. 1 inch is that size. 1 inch long and zero point 0.1 inch in diameter. So these details are there in your textbook also. This point. And an important thing is that about this filament is that this filament has to be preheated. So first we'll heat this filament, then we apply the current. So once it reaches the hot temperature, that is when it is becoming to that red or white color. After that, we apply the current in order to make that hotness constant. Okay. Until that, we have to heat this filament. So preheating is important with this filament. Okay. So preheating is important. So first we have to heat that filament by using some other method, and then we have to apply the current. And once it reaches the red or white color, then we have to apply that current, and then the current will make the temperature constant or the hotness. Okay, so that is the that is associated with the Nernst filament. It's all about Nernst. Now we will discuss about the second filament. Okay, two different filaments they can use in IR spectrometer. They are using in IR spectrometer. The second one is Glauber filament. Second one is Glauber filament. So in this case, a rod of carborundum, a rod of carborundum this one is thicker and longer than Nernst filament. So a rod of carborundum is used as a Glauber filament in Glauber filament, and this is thicker and longer than the Nernst filament. Okay, so these two filaments are the source of IR radiation. We use different filaments as an IR source in spectrometer, and these two are the normally using filaments in IR source. One is Nernst filament, the other one is Glauber filament, and in Nernst filament we have a spindle of rare earth oxide of about 1 inch long and 0.1 inch in diameter, and this filament has to be preheated. Okay, before action, the spectral analysis, we have to preheat the Nernst filament. Then we have to, once it reaches the red and white hotness, then we have to apply some current to maintain that. So this Nernst filament has to be preheated, but Glauber filament we do not have to preheat it. We will increase its temperature and hotness by applying that current itself. A rod of carborundum is used as Glauber filament, and thicker is thicker and longer than that of comparing that with. Now another important section or part of the IR spectrometer that is optical path and monochromator. Optical path and monochromator. So considering this optical path and monochromator, normally we know that optical path is means that we have to focus the IR radiation into that sample. That is what kind of techniques we use, mirrors, we use lenses, all those things, optical components to focus the IR radiation on the sample. That is the meaning of optical path. A monochromator means that we have to make that IR radiation into some particular frequency at some particular time. So that is that can be done by using some. So we have optical path, different path we have to consider, and we have to focus the IR radiation to the sample. So in order to do that, we use the different lenses, mirrors, all those things. That all these components will come in the path section. So the beam is guided and focused by mirrors, silver. So I will just write it as point. Okay. Beam is focused by using mirrors, silver by using mirrors silvered on their surface. Instead, on the surfaces of this mirror, we have this silver coating, and we control that reflectance, transmittance, all those things by using this silver coating. Some of them will be half reflecting, some of them will be full reflecting like that. So beam is focused. Uh, beam is focused by using mirrors silvered on their surface. Okay, that is first point. So beam is focused by using mirrors silvered on their surfaces. You can write beam is focused on the sample by using mirrors silvered on their surfaces. Okay, so in this particular IR spectrometer, ordinary mirrors can't be used. Not be, that cannot be used ordinary mirrors cannot be used as uh, they absorb IR radiation. So normal mirror, if you consider normal glass, they will absorb the IR radiation. So we have to use some other type of glasses. Okay. So any windows must be made of mineral salts. Made of mineral salts. That has to be mineral salts. Transparent to IR radiation. Okay. So normally we use the NaCl, that is rock salt, and KBr, potassium bromide. Okay, these two are normally used. These two materials are normally used. Okay. And this so which are highly polished. In order to reduce scattering. So in order to reduce the scattering, we have to polish these KBR and NaCl windows very finely. Okay. Then only we can reduce the scattering to the minimum level. So normal glass windows we cannot use because glass will absorb air radiation. So that we cannot use. So we have to use NaCl and potassium bromide windows mirrors in this IR spectrum. And in some instruments, prism made of rock salt or potassium bromide is used as monochromator. So this is the section of optical path. So we will discuss about the monochromator in the same section. So in some instruments, uh, prism, and this prism will be made up of NaCl or KBr. Use or I can write this as a monochromator. Okay. So rotating this prism in different angle will provide the desired frequency. Okay. So rotating prism desired like, in different angle different angle uh, will provide desired frequency. Okay. And in modern instruments, modern instruments means that modern IR spectrum, IR spectrometer. In modern IR spectrometer, we use rotating grating. Rotating grating act as monochromatic. So as compared to the prism, this monochromator's rotating gratings will be having high resolution compared to, prism. If you compare that with prism, we have high resolution for rotating grating. So we use grating that will be rotating uh, at different angle. When you rotate that at different angle, you get different that will be focused at the stand. So this is the monochromator. These are the monochromator which we use. Old instruments we use, old IR spectrometer we use prism, and by rotating that prism, we'll get a different IR spectrum. So that means that if you're having this grating somewhere here, or I will just say that with prism first. So if you're having that prism somewhere here, and you are having some that all the frequencies which are coming. This is this particular incident radiation is having all the frequencies, some range of IR, for example, near IR. Okay. So in that case, we have different frequencies which are coming and hitting at this prism, and that means a particular band of frequencies coming and hitting this prism, and that will be dispersed by using this prism. So if you are changing that angle of prism, you can change the direction of these frequencies which are coming out from this prism, and you can focus that on the mirror or something where we will use in our spectrometer, and you can focus that particular frequency into the sample. So that is the technique that we use. Otherwise, you can use the monochromator as your weighting. Weighting also do the same technique by rotating with a different angle. We can have different frequencies, but the frequencies that comes out from the grating will be much higher than that of the prism. So we can resolve different frequency components into single frequencies by using the weighting. The efficiency of that resolving power. Resolving efficiency will be much higher in case of grating. So we can have different, much more larger frequency components by using grating as this. So that act as a monochromator, and then we have the detector. That is the last part of the instrument. So we have detector. We do not have much. There are two main types of detectors. Two main types. One is called as sensing heating effect. Heating effect of radiation. Second method is that depends on the photo conductivity. So in these two cases, for example, in both cases, greater the effect, the greater will be the transmittance. In both cases, greater the effect, greater will be the transmittance. What this means that if you are considering these two, okay, if you are having larger heating effect by using this radiation, then you will be having larger transmittance. If you are having a larger number of photocurrent, number of photons, photoelectrons, larger number of photoelectrons, then we have larger number of photocurrent. Sorry, not number, larger photocurrent or higher photocurrent. Okay, and also correspondingly we have larger transmitter. So what that means is that if that monochromator will produce one single frequency, okay, almost single frequency, and that will be hitting this sample. Okay, and if the sample does not having that particular frequency of vibration inside it, there is no group which is associated with that frequency of vibration, then that frequency will just pass through this sample and hit this detector. Okay, detector here. So this detector will be detecting this particular IR radiation by using two techniques. Two techniques. One is sensing the heating effect of this IR radiation, or by using photoconductivity. So in both cases, if this IR radiation coming and hitting on this particular detector, if the heating is larger by this IR radiation, then we'll be having higher transmittance in your spectrum. So the transmittance will be maximum. Okay? Your transmittance, your transitions will be. If the heating effect is smaller, which means that some of these frequencies are absorbed by the sample, then your transmittance will be smaller. So that will give you a spectra corresponding. Or similarly, if your photoconductivity, if you're considering this detector with a photoconductor, and the IR radiation which is hitting on that particular detector will produce some electrons, and photoconductivity will happen. And then measuring that photocurrent, if that is larger, then we'll get a transmittance which is higher. Okay? If it is smaller, then we'll get a transmittance. So we'll get a spectra like this at the end, a transmittance. So that is the method that we'll use. Two methods we'll use in the detector part. And by heat sensing, for heat sensing, we will use different techniques. So heat sensing. So heat sensing means sensing the heat produced by the IR radiation which is coming out from the sample. So by heat sensing, for heat sensing we use different detectors. One is Golgi cell, and this Golgi cell is radiation. When the radiation falls on this particular cell, uh, that contains air, like that cell, and the temperature change is measured in terms of pressure change within that cell, and that is recorded as transient. So in this cell, the radiation falls on small cell containing air. Okay, and the temperature is measured by, or we can say in terms of terms of changing pressure that is recorded as the transmittance. So basically, when the IR radiation falls on this Golgi cell, there will be a pressure change, and that pressure change is detected of what is the change in pressure inside the cell, and that will be the corresponding transmittance. So the temperature is measured in terms of pressure change, and that is recorded as the transmittance. So that's about the principle of Golgi cell, and then we have some other techniques also. This is thermocouples we can use here to detect the temperature. Otherwise, we can also use meter. All these things are to measure the temperature, very small temperature we have. And then we have next one, that is by photoconductivity. So for photoconductivity, for this sensing, photoconductivity sensing. So for by this sensing, we have to use different photoconductors. Okay, are a particular class of cell. This photoconductor is a particular class of cell. This energy required that is coming from this incident radiation, and the material like lead sulfate are very sensitive to this IR radiation, so we can use that as a photoconductor. And the conductance of the material can be measured by a type of like Wheatstone bridge network, and when plotted against the frequency, this is directly the transference of this. So in this case, we use different photoconductors. Okay, so photoconductors. So these are the special class of semiconductor. We already discussed about photoconductors first semester itself. So photoconductors sensitive to IR radiation. And one example for this is lead sulfate. Sorry, lead sulfide. Not sulfate. Lead sulfide. Okay. So the conductance also the conductance is measured by a Wheatstone Wheatstone bridge. Wheatstone bridge network. And plotted against frequency as transmittance. This current is plotted against frequency as transmittance. So that current also will be proportional to transmittance, so it can be plotted against that frequencies. And we will get. So we already discussed about the source, then monochromator, as well as detector. Now we will cover last one, which is the sample. So in IR spectrometer, which kind of sample we use, or what, how we will prepare the sample, all those things we will discuss in this section. So first thing is that this sample is held between plates of polished mineral salt. In IR spectrometer, sample is held between plates of uh, polished mineral salt. Okay, so we cannot use normal silica glass, but we can use different mineral salt like NaCl or KBr, potassium bromide. Those materials we can use. These materials are normally using as windows and glasses in air spectrum. So such kind of two plates we can consider two plates with the KBr or NaCl, and within between these two plates we will place our sample. So in between these two, place our sample, and then the radiation comes and hit with this sample. So this polished between these polished uh, plates of mineral salt with KBr or NaCl, will be placing that sample in between those plates. Okay, so that is first thing. Second point is that pure liquids are studied in thickness of about 0.01 millimeter, while solutions are studied with zero point 0.1 to 10 millimeter. So if you are considering pure liquids, if you are considering pure liquids, then these pure liquids are studied with a thickness of zero point 0.01 millimeter, which means that if your sample is in pure liquid form, okay, which is not a solvent, which is in pure form of liquid, okay, in that case, it can be made having a thickness of 0.01 millimeter. So it will be placed in between these two plates with a thickness of 0.01 millimeter. Similarly, if it is a solution, if it is a solution with the solvent and solute, then we will be using with the thickness normally with the thickness of 0.1 to 10 millimeter in size. Okay, and the third point is that the gas samples at pressure of 1 atm. So in this case, the gas samples. So the gas samples with 1 atm pressure. Okay. These gas samples that they can be usually contained in a glass cells, either 5 or 10 centimeter long, closed on their ends with rock salt. And also special long path cells in which radiation is repeatedly reflected up and down. That is considered with for gases which are having lower pressure than this 1 atm. Okay, so if the gas is having 1 atm pressure, then we use we will use this will be contained in glass cell glass cells which are 5 or 10 centimeter long and closed on their ends with rock salt mineral. So considering this case with the gas samples, we have to use glass cells. Okay? And in that glass cell, their windows will be closed. Okay? This will be 5 or 10 centimeter long cells, but their windows are closed with the rock salt because through that window we have to send the IR radiation. So it will be like so these two are windows windows of this glass cell, and the gas will be inside this glass cell, and these windows are made up of KBr or NaCl oxide, calcium bromide. So we have to use any oxide. In this case, the gas is at 1 atm pressure, and we have to send radiation through these windows to these gas samples, and there will be detector after that. Pass through this. So that is the method for gases, material or sample in gas states. And there are some other case when you are having gas with low pressure. So gas samples with pressure less than 1 atm. So in this case, when the the gas sample pressure is less than 1 atm, then we have to use glass cell, very long glasses. Okay. So in that case, we use special long path cell. Okay. So this long path cell produce repeated reflection of the radiation. Up and down in the cell. So when the pressure is low, the gas pressure is low, we use very long cell compared to the previous one. Will be having very long. These two sides will be equal. And the radiations will be moving like up and down through this. Basically, it has to interact with the sample also. When the pressure is low, the molecules of the sample that we have to study will be moving randomly. So the radiation may not hit on those molecules if it is going directly through that cell. So a random motion of the radiation is preferred. So in that case, we need a very long glass cell, and this kind of multiple reflection, repeated reflection will be happening in the cell, and the possibility of interaction of that particular radiation with the molecule is possible when you are having kind of repeated reflection. Otherwise, if the molecule, the sample pressure is low, very low, and the so the molecules may not interact with the radiation because the molecule have more space in the cell, and it can move randomly. So if you are sending the radiation in unidirection, then there is possibility that that radiation may not interact with the molecule, or the interaction will be very less, and the transmitted signal will be higher, and we get very low intense spectrum. So because of that, when the gas pressure is smaller, in order to make interaction between this radiation and molecule which is in the sample, we use some multiple reflection or repeated reflection technique in the cell, so that it may increase the possibility of interaction of sample with the Okay, so that is for gas state. When we have gas sample of lower and higher pressure. Okay, now we will discuss the case with the solid samples. So we discussed about with the liquid sample as well as gas samples. Now we will discuss about solid samples. For solid samples, it is very difficult to examine the spectra because they reflect. First of all, they reflect and scatter the incident radiation much more as compared to the liquid and gaseous states. So the transmittance will be very low because of this scattering effect and the reflection when you use the solid sample. Okay, so I will just put that in here because of scattering and the reflection. The transmittance, the more with the solid sample. So the transmittance means the output signal intensity we are talking about. So the intensity will be very small because already if you are sending IR radiation to these solid samples, there will be scattering, there will be reflection of that particular wavelength. So many of the radiation will be scattered away from the sample, and many of the radiation will be reflected back. So very few radiation will be transmitting through the sample. Okay, so the intensity of the transmitted spectra will be small in the case of solid samples. So it is a little difficult to examine the spectra because the intensity is low. So we have to reduce the scattering when you consider solid samples. So in order to reduce the scattering and reflectance, we need some additional methods with the solid sample preparations. So first one is that in order to make this solid sample, if the solid cannot be dissolved in suitable solvent, it is best examined by grinding it very finely with paraffin oil, and this forms a suspension, and this can be held between the rock salt window, provided that the Pfeffer index of the liquid and solid phase are not very. So that is the first method. So this is only applicable if the solid cannot be dissolved in any solvent. So if solid cannot be dissolved in any solid, sorry, solvent, then best method is to make or best method is to grind the sample with paraffin oil and make suspension of the same. Or so this has to be method is to grind the sample with the paraffin oil finely, and this forms this forms suspension, and this suspension can be this can be then placed between rock salt. Salt means that we, in the case of liquid, we have that rock salt plates. So in between that, we can place this suspension. So what we have to do is that we have to grind the solid sample with the paraffin oil. Okay? We have to use that pistol and mortar and grind it very finely. Then it will form a suspension like in the suspension form, that suspension state. And then this suspension can be placed in between that plates of salt. Okay, then we can examine the infrared spectra of the sample. Remember that in these methods, when you are using solvents, the solvents, which means that our sample will be the solute, and we have to use some. I think yes, in the case of solutions, okay, this will be consisting of solvent as well as plus solute. So normally we'll be using the sample as our solute, so that this two will make that solution. If that solute is, for example, a solid sample and which cannot be dissolved in any kind of solvent, then we have to go for this grinding with the paraffin oil. If it is solvable in some solvents, okay, so then we have to use this solution method. And in this solution, we have to study the IR spectra of the solvent, solute. Then we have to know what is the IR spectra of solvent. We can subtract them by using the IR spectrometer, because we are storing the data in computer system. We can easily subtract solvent from the total IR spectra. Okay, then we'll get solvent solute IR spectra. Okay, that is also can be done by the FTIR spectrometer. That's another advantage for using. So this solution consists of solvent as well as solute, and solute most probably uh, will be examining the solute, okay, the IR spectra of the solute. So in that case, we have to remove the solvent IR spectra, IR peak, after evaluating the IR spectra of the solution. But sometimes the solvent and solute will be having the same uh, frequencies of vibration. Okay. In that case, we have to analyze the total spectra, and we have to analyze what are the different frequencies which is coming from the solvent itself. Okay. So that is also important. So analyzing IR spectra is another important section that we are not going to cover in this syllabus. So that is also there. Okay, so but we can also remove the solvent if you know that the solvent, because in some cases, for example, if you are having this white stretching vibration or any other vibration which is associated with this core, And suppose if this OH bond is present in both this solvent as well as solute, okay, so we will be having spike or spectra which is corresponding to the OH bond in the solvent as well as in case of this solute if it is present in both cases. So if you are examining the spectra of that solution, then the intensity of this particular beam will be larger because some vibration coming from solute as well as some coming from a solvent. So the intensity will be larger. So when we are subtracting that by using the this computer system, because when you are using FTIR, we have already stored all the data. So we can easily subtract the intensity of solvent and solute, and then we'll get the exact spectra corresponding to solute. That is the method that we'll use to get the spectra of a particular sample. In some cases, we can also, for example, if you want uh, to, to have a confirmation that this solute is present in this particular, then we do not have to take it separately from the solution. We can just examine, then we can analyze different frequency of vibration, then we can conclude that this particular sample. Otherwise, if you are making some new sample, then we have to separate it from the solvent. In that case, we have to use this separation technique by using the computer system. That is the so if the solid sample is not dissolvable in any solvent, okay, we cannot make any solution. In such cases, we have to go for this method that the sample solid sample has to be grinded with paraffin oil, okay, and that will make a suspension form, and that suspension we can use and place in between those rock salt windows, and the IR spectra can be studied. And in that case also we have to subtract the IR spectral intensity which we can store in the system, in the computer, and we can subtract that from the suspension. Then we will get the spectra corresponding to the solid sample. Okay, because the suspension consists of paraffin oil. This is paraffin oil plus sample. Okay, so we will be getting spectra for paraffin oil plus sample when you use that particular configuration. So then we have to subtract the spectra corresponding to paraffin oil that we can load into the computer after studying what is the spectra of paraffin oil alone, and we can subtract that from the spectra of the suspension. Then we will get the spectra corresponding to our sample. This is the method when you are using when your solid is not dissolvable in any solution or any solvent. And in this case, one more thing uh, you have to check is that the refractive index of this uh, suspended suspension, or the refractive index uh, of the liquid and solid phase, if you are considering both phases of this sample, that should not change very much. Okay, that's why we are using this particular parameter, like this suspension, and it should not. When you are mixing these two, the refractive index should not change very much. Uh, so we have to choose accordingly. Normally, we use this paraffin. And second method corresponding to this solid is that we grind the solid very finely with the caviar. So in this case, we do not use this paraffin oil, but we grind the solid sample with KBr, that is potassium bromide, okay, finely. So fine powder like we will get from this after grinding. So this is just like a powder. It will be just like a powder. Solid plus KBR. Okay. Then the mixture can be pressed into a transparent disc. And then the mixture, that is sample plus KBR, will be like a powder form. So this mixture can be pressed pressed into a transparent, transparent disc. Okay. And this may then placed the IRB in a suitable folder, sample folder, suitable folder. So what that means is that we have to put this in that. So if you want to know about this method, you can search for pellet preparation for IR spectrometer. There are many YouTube videos with that. So that is pellet preparation. So this disc, okay, pressed into this disc, and this disc is called as pellet. Let me check this pellet. And this method is the called as pellet preparation. Okay. So what we have to do here is that we have to take that pistol and motor, just, or you can just check that video. So we have to grind this uh, KBR plus our solid sample, okay, by using this pistol and motor. So we have to add this KBR, that is potassium bromide, as well as the plus solid sample into this pistol and motor, and then grind it very finely, and it will form some powdered form. And that powdered form, then you place it in some, there is some setup. Okay. There will be some brown light. Okay. So this I cannot draw, and we will apply some very high pressure from above. So this will be coming. Our sample will be placed in this like structure, and it will be in powdered form. Okay. So uh, this will come with high pressure, and that will form very fine disc-like sample structure with very thin. Okay. So the thickness is very small, and it will be transparent. So this is like, so you can check that video, okay, like this, and our sample will be placed inside this, and that will be pressed. So this is just a schematic diagram. Okay. So this will be coming from above with very high pressure, and which will be pressing that sample which is in powdered form. And because of that high pressing, the sample will be formed like a disc-like structure, and this disc-like sample will be placed on the some particular holder in that IR spectrometer, and the IR spectra will be passing through palette. So this is nothing but a palette, and maybe it is not exactly like this. So the sample holder will be there, and the palette will be placed up and down or something like that. depends on how the uh, sample holder is. So this is just a schematic diagram of the same. So IR radiation will be passing through this. Okay. So normally we will be having some disc-like structure, very hard metal, and the sample will be prepared in this. So this is the pellet formation, and the pellet is nothing but this is very hard, very hard. And when you press that sample inside this particular very hard ring, sample will be inside this ring, and this is the sample. So this sample also will be inside that ring. So this is our holder, sample holder, and that has to be placed that that IR. So that IR radiation will be passing through the sample, and this sample is nothing but KBR plus your solid sample. So some of the radiation will be absorbed by these solid samples, and that can be, and there can be some small spikes corresponding to KBR that can be uh, avoid or that can be removed after receiving total estimate. And solid corresponding to the solid sample, we will get different versions. So you can watch that videos on YouTube, or I will show that in the next class how to make these pellets. pellets. So this is the second method to form the to examine the solid samples using the IR FTIR spectrum. So that's all about the sample. So we discussed about liquid sample, we discussed about gaseous sample, and also we discussed about solid sample, how